So far in our course, most of the time we looked at the system of linear equations of kind Ax equal to b, where b was not necessarily 0. So the right hand side of the set of equations was not necessarily 0. But we did look at some cases where b was actually 0 when we were defining the linear independence of a set of vectors, remember? This is in chapter 8 actually. So if you have a bunch of vectors as the columns of a matrix A, Ai, and if you can find a particular linear combination, the numbers, the scaling factors not all 0, such that the linear combination is 0, then the columns of the matrix are not linearly independent. So this we actually said. So the definition of linear dependence is that you would be able to find some set of numbers x, not all 0, such that a linear combination is equal to 0. So that basically, if you look at xi times ai as linear combinations of the vectors ai, and if you put the ai's in a matrix, that basically reads ax equal to 0. If you can find ax equal to 0 without x being a 0 vector, then the columns are not linearly independent. Now, the set of all such vectors, non-zero vectors, well, including 0 also, but non-zero vectors, would be the solution set. And that set is called the null space. So a null space will always have the 0 vector because ax equal to 0 when x equal to 0, trivially, all the time. But if you can find some other vectors, non-zero vectors, that also will be a part of the null space. Here is a definition: null space of A. Null space of A is a set of all vectors x such that ax equal to 0. It's a solution set of the homogeneous system of linear equations ax equal to 0. Now, one thing to note is that if there are two such vectors in the null space, if you have x1 such that ax1 equal to 0 and x2 such that ax2 equal to 0, then any linear combinations of x1 and x2, so that also will be a part of the null space x1 equal to 0, because x1 is a member of the null space of, so is x2, which means ax2 also equal to 0. I can multiply the first one by some scaling factor s1, second one by some scaling factor s2. That wouldn't change the right hand side because it's already 0. Add them up. That will basically give me a times s1 x1 plus s2 x2 equal to 0. That means s1 x1 plus s2 x2, a times that vector equal to 0. So that has to be a member of the null space of A. So what we used here is the fact that the scalar multiplication commutes with the vector multiplication or matrix multiplication. In other words, SA is the same as AS. That's what we used in being able to go from here to here. So since the linear combinations are all in the null space, it means that null space really is a subspace. If it was not closed under the process of taking a linear combination, then it wouldn't be closed under the process of under the basic operations of vector spaces. Then it would not be closed. We would not be able to call it a subspace. Now, what I'm proving here to you is the fact that the null space really is a subspace. Remember, null space is not a linear combination of anything really. It's actually a solution set. Each vector in the null space is of the kind x, the variable vector. So if you have a matrix of size m by n, then remember x is a member of Rn, because the number of components in x, number of rows of x, is the same as the number of columns of A. This n, so that you can do the multiplication, confidity of multiplication. So x has as many as the columns of A. So x is a member of Rn. The null space of A is a span of all such vectors. So the null space has to be a subset of Rn. Now, if you think about Ax equal to 0, so what I have is Ax equal to 0 because x, I'm thinking of x in the null space of A. Now, let me write A as a bunch of rows, not as columns. Let me think of as rows. I have, so that's my matrix A. And if I'm thinking of Ax now, x is here, and I'm saying that is equal to 0. What is 0? That is a vector of m elements also, 0, 0, all the way up to m to 1, m of them. So that's the way it is. So I can read row by row here. So what that means is R1 transpose x. So R1 transpose x is equal to 0, the number. The second one would be R2 transpose equal to 0, and this, and so on. In general, what I have is something like Ri transpose x to 0. That means x is orthogonal to every single row in A. So x is a special vector. If x is a member of the null space, then it actually implies that it's actually orthogonal to the rows of A. Now it is orthogonal to all rows, then it's orthogonal to a linear combination of them all also, because I can multiply this guy by S1, this guy by S2, and this guy in general by SI, and then I can sum them up. So I'll get something like I running from 1 to M, I transpose. Okay, that is my first entity. That is a linear combination, SI RI transpose. That is my linear combination multiplied by X and sum of the right hand side, which is just 0. So X is orthogonal to all linear combinations of the rows of A, or possible linear combinations. So my SI here can be any number. That would be the span of the rows of A. That would be orthogonal to my X vector if X is a member of the null space of A. Now the span of the rows of A, the set of all linear combinations of A, I'm going to call that the row space. That's going to call that the row space of A that is perpendicular to the null. So that's what I'm trying to say here. Ri transpose times X is actually 0, and then all linear combinations will also give me 0. Now instead of calling it the rows of A, I don't really like it because remember vectors are always columns, which is why I wrote Ri transpose. So I can take a row of A and then takes its transpose, or I could just transpose the whole matrix A and then look at the columns of the transpose. So the rows of A are row matrices, or a better way of looking at it is to say that the columns of A transpose, they are orthogonal to my X. So the linear combination of any possible linear combination of the rows would be orthogonal to my X as long as X is a member of the null space, and the set of all such linear combinations is what we will call the row space. The span of the rows of A, or the span of the columns of A transpose as a subspace, that will be orthogonal to the subspace that is the null space. Because what's the definition of orthogonality of two subspaces? If all vectors in one subspace are orthogonal to all vectors in the other subspace, then these two subspaces are orthogonal to each other. That's what we just learned about the row space and the null space. So the row space is the span of the rows of A, is a set of all possible linear combinations of the rows of A, or it's also the span of the columns of A transpose. You will reuse the symbol column space, but it's a column space of A transpose, which is a row space of A. Now remember, just like the column operations did not change the column space, the row operations will not change the row space. So if you want to find the basis for the row space, you could say take the pivot rows of the matrix, the linearly independent rows of the matrix A, or you could take the pivot rows of its REF or RREF, because in order to go from A to its REF or to its RREF, all we are doing are just elementary row operations which do not change the row space. The significance of row space. So again, let's take our favorite matrix, M rows and columns, rank is R, and if you think about AX equal to B, what is it doing? It's taking a vector X and giving you a vector B. So the input is X, output is B, but the input vectors belong to Rn. Each vector X has n components, so they belong to Rn. The output vectors B, they belong to Rm, same as the number of rows of the matrix A. So it's a mapping from R to Rm. That's one way of looking at it. Now we already saw that if you have null space, that is the collection of all possible solutions of Ax equal to 0, which means vectors in the null space will go to the 0, 0 vector. If you take an x in the null space, Ax is going to be 0. So vectors in the null space will go to B equal to 0. So vectors in the null space will map to 0. And then vectors in the row space will map to something that is non-zero, which will be a linear combination of the columns of A. All such linear combinations will be in the column space. So vectors in the row space will go to the column space. If it was 0, then it would already be in the null space. It will go to the non-zero elements of the column space. Now, we already saw that the row space is orthogonal to the null space, but it's actually better than that. It's actually orthogonal complement. They are actually orthogonal complements of each other. So we did not prove the complement part. Remember, orthogonal complementarity means orthogonal complement is the collection of all possible orthogonal vectors to the vectors in the subspace. So take my word for it for now that the row space is not merely orthogonal, it's actually the orthogonal complement of the space. And remember, the row space being the linear combinations of the rows, each of which has n components, and null space being the linear combinations of the solutions, each of which has n components too. They both belong to Rn, and the fact that they are orthogonal complements will mean that the dimension of row space plus the dimension of the null space will be equal to the dimension of the containing space, which is n, the number of rows. Now, what's the dimension of the row space? That is the number of linearly independent rows of the matrix A. What's the number of linearly independent rows of the matrix A? Is the rank of A. So this guy is the rank, and this guy, the dimension of the null space, is called the nullity. So that is the rank-nullity theorem, that is saying that the rank of a matrix plus its nullity is the number of columns of the matrix. The number of linearly independent rows of A is the same as the number of linearly independent columns of A. So rank is also the number of linearly independent columns. So one way of stating the rank-nullity theorem is to say that the number of linearly independent columns of A plus the dimension of the null space is equal to n. That, I think, is the way people usually say it. So rank plus nullity is equal to n. That is the famous rank-nullity theorem, which is like the cornerstone of linear algebra, one of the fundamental foundational theorems in linear algebra. Now, there is one more thing I want to show you before we move on to an example, which is this. Suppose I take a vector that is in the row space, and suppose I take another vector that is in the null space, and I add them up. So x parallel is in the row space, x perpendicular is in the null space, and I add and then multiply by a. What's going to happen? A multiplication will distribute into the summation, so that is ax parallel plus ax perpendicular. But ax perpendicular, x being a member of the null space, that is going to go to 0. So there is nothing there. Whenever you add a vector from the null space, it doesn't change the right side of the equation. This has got some relevance to the fact that you have infinity of solutions, etc. You have infinite number of vectors in the null space. You add any one of them to the vectors in the row space, and the right hand side doesn't change. So let's actually look at an example here. Suppose I take a matrix, its simplified version, because it's basically identity matrix in which I killed element in the row number 3, column number 3. What's the rank of this matrix A? It is 2 because it's got 2 linearly independent rows and columns, but better than that, it's got 2 pivots right in front of you. They're actually unit pivots. What's the row space of this matrix? In order to find the row space, I have to find the linearly independent rows, which will be this row and this row. So if I want to say what the row space is, I have to know what the containing space is. Each row is got 3 components, okay, and the rank is 2. So the basis vectors will be the pivot rows, so the basis would be the pivot rows, this row and this row. So the first one is going to be 1, 0, 0. So that is 1, 0, 0, the pivot row, but as a column. And then one is 0, 1, 0, 0, 1, 0. So those are the basis vectors. And the dimension is 2 because my rank is 2. Now, how do you find the null space of this particular matrix? Now, in order to find the null space, you have to think about ax equal to 0. So I have to multiply by some x here so that I get 0. One such vector would be 0, 0, some value z. So what happens if I multiply a with that? I get 0 of the first column, 0 of the second column, z of the third column. But the third column is already 0, so that is going to be equal to 0. So any vector of the kind 0, 0, 1, 0, 0, 2, 0, 0, 5, all those things will give me ax equal to 0. In general, I can say that the null space, again, will be vectors of the kind x, will have 3 components, number of elements, number of unknowns, and the dimension is 1. Dimension is 1 because we can find only one solution. The basis for that is 0, 0, z, but might as well normalize it and call it 0, 0, 1. Now, this is all fine. The reason I wanted to show you all this thing is we can visualize this. What is the basis for the row space? It is 1, 0, 0 and 0, 1, 0. If you think about it in coordinate space, what do you have for 1, 0, 0 and 0, 1, 0? What are the linear combinations of those two guys in a normal XYZ space? 1, 0, 0, 1, 0, 0 is a vector here, that is my x-axis, and 0, 1, 0, that is my y-axis, and my row space C of A transpose was had the basis these two vectors. So my row space is all of this space, all possible linear combinations of my null space. I said the null space was had the basis 0, 0, 1. I'm writing it properly as a set because the basis is actually a set of vectors, and that vector is actually along this axis. So as you can see, the z-axis is orthogonal to x and y plane. All vectors on the z-axis are orthogonal to all vectors on the xy plane. So take a vector on the xy, some vector in some direction in the xy plane, and that is always orthogonal to the z-axis vectors on the z-axis. Similarly, if you take some vector on the z-axis, some scalar multiple of that vector, that's going to be orthogonal to all the vectors on the xy plane. More than that, if I find any vector that is orthogonal to the z-axis at all, that has to be necessarily on the xy plane, cannot be anywhere else. And if I find a vector that is orthogonal to the xy plane, it has to be along the z-axis, it cannot be anywhere else. But in linear algebra, all our vectors will start at the origin. So this is my row space here, my row space here, and my null space, and they are orthogonal complements of each other. If I take the union of these two guys, just row space, union, null space, that will be all the vectors on the xy plane plus the vectors on the z-axis, but that is only a tiny part of the space. There are many other vectors in some random direction, not on the z-axis nor on the xy plane. Most of the vectors in the space are actually not on the xy plane nor on the z-axis. They're all linear combinations of these guys. So if I call a vector on the xy plane x parallel and vector along the z-axis x perpendicular, all such vectors will describe all of R3, because if you give me any vector in any direction, I can find the right weight of that along some x parallel and some x perpendicular, so I can describe that. And what I was saying is that if I multiply this by the matrix A, if I transform this combination by A, what will happen is that this will become A x parallel plus A x perpendicular, but x perpendicular is in the null space, remember. So this guy will go into 0 vector, and that becomes just AX. So that's what I was trying to say. In other words, take any vector, any non-zero vector in R3, which will be of the kind this, and multiply that, transform that using the matrix A. That will be a linear combination of the columns of A, which means this will go to my column space of A. So that's what I was trying to say. So all vectors will go either to the 0 vector if it is in the null space, or go to the column space. So that's all I said. So the row space was really orthogonal complement of the null space in that case, because I showed it to you. All vectors on the row space xy plane are orthogonal, and there are no other vectors that are orthogonal to the row space that are not in the null space. That is the definition of orthogonal complementarity. So I gave you 3 statements.